What if I told you that the smaller a house is, the more expensive it will be? As outrageous as this sounds, this is actually the case across the United States, Europe, even in Israel. The explanation is actually pretty simple. Rural, inexpensive areas tend to have larger houses, whereas urban, expensive areas tend to have smaller ones. Of course, if we looked within these groups, we'd find the opposite trend that, sadly, bigger houses do cost more. This, as some of you may have noticed, is a classic example of Simpson's paradox, where the relation between two variables differs when looking at the population as a whole, as opposed to subpopulations within it, because of a confounding factor. But I'm not here to talk about Simpson's paradox. What I'm interested in is, how do we determine these subpopulations? Do suburban towns act more like the countryside or the city in their size-price relation? Or should they be treated separately? Our clustering criteria has to be very specific to the problem. Cases like these are extremely common and important in making real-life decisions. So today, I'm going to walk through a clustering search algorithm that is useful in these cases, among others, where the clustering criteria is non-trivial. And I will show how using the specifics of my problem to my advantage allowed me to fully solve it in ways I otherwise could not. I will talk about a case where dynamic programming met clustering, and hopefully in the process convince you of the merits of second-guessing the way we typically match problems to solutions. And I promise, once we get through this, there is food waiting on the other end. Bear with me. But before we dive in, my name is Maya Samuels. I'm very excited to be here. I've been a data scientist at VIA for nearly 2 years, preceded by a master's in climate modeling and a bachelor's in physics. At VIA, we are on a mission to bring technology to public transportation to solve global problems such as congestion, pollution, and equality in mobility. We develop and provide software that puts vehicles where they are needed, groups riders going in the same direction, and plans on the go based on traffic and demand. My work at VIA is focused on traffic modeling for VIA's planning, ETA, and routing needs. Though the work that led to this talk is from my time at VIA, the specific VIA use case is not the focus of this talk, which is about a much broader problem and approach. So let's talk about clustering. Clustering is the bread and butter of data science, but just so we're on the same page, clustering can generally be defined as grouping a set of objects in such a way that objects in the same group are more similar to each other than to those in other groups. But the way we define this similarity can vary a lot depending on our choice of the loss function, to the point that we may not really mean similarity per se. The loss function can be thought of as a formulation of the criteria by which we would like to cluster, and it has its minimal value for the optimal solution. It is typically related to distance or density in the feature space, but it doesn't have to be. Clustering being the common and useful tool that it is, and I think we saw a few examples today in the talks of this session, has lots and lots of out-of-the-box solutions. They are quick, simple, and robust to use, but they are also limiting and don't always fit the complex problems we meet in our day-to-day work. I had such a case. Its most important characteristic was that I wanted to choose my own loss function. These out-of-the-box tools optimize on a predetermined loss function in relation to feature space, often using gradient descent methods which require the loss function to be smooth. My loss function was not necessarily differentiable or continuous or directly related to feature space, or limited in almost any other way for that matter. Another characteristic of my problem was an unknown number of clusters. Many of these algorithms require you provide this as a parameter, but it was central in my problem to optimize not only for the values of the clusters, but the number of them as well. I had a single sequential feature by which to cluster, and I wanted to allow for small, noisy, and partial data sets. On that note, it's important to keep in mind, like in any data problem, that the result will heavily depend on the data, and the same physical phenomena can look very different in different data sets. If my data were dense and had a robust and continuous relation to the feature, the best clustering solution would be something like point estimates or the maximal number of clusters we allow. If, on the other hand, the data were sparse, or its relation to the feature did not have any statistical significance, the best clustering solution would be no clustering at all, or a single cluster for the entire feature range. So what kind of problems does this describe? Well, one might be age-based health insurance. How do we divide the human lifespan to best estimate the distribution of health expenses of all patients? Another could be income tax. How do we bracket income to create an equitable but financially viable system to cover the government budget? Yet another is time-based traffic modeling. How do we predict the seasonalities, such as time of day and day of week, to best estimate the speeds across all roads in a city? But really, any pre-clustered modeling where the clusters need to optimize for the subsequent model and not simply for similarity within the feature space, as we saw in Simpson's paradox. In our house example, we needed to cluster not by similarity of price and size, but rather by their relation to the confounding factor to municipal type. All of these examples have in common a non-trivial criteria by which we would like to cluster. So now that we're motivated, how do we solve this problem? And by that I mean, which search algorithm will allow us to find the optimal clustering solution? We are free to choose almost any loss function, as we defined in our problem requirements, but I will not discuss the choice and design of this loss function, which is specific to each problem by definition, and therefore not the focus of this talk. Instead, we will ask, what is the search algorithm that will allow us to find the fully optimized solution in reasonable runtime without limiting our choice of the loss function? Since we don't assume anything about the loss function, we can't use methods that scan only part of the solution space, meaning the number of solutions we have to consider is 2 to the power of the number of possible individual clusters. For age-based insurance, that would mean considering every combination of, say, 100 years of lifespan, 2 to the power of 100 options. The computation time for that would diverge very quickly. Even if all we had to consider were these 7 Simpsons characters, we'd have to consider 6 options for 2 clusters, 15 options for 3 clusters, 20 options for 4 clusters, and so on, for a total of 64 options, and that's if we had 7 data points. At this point, we could turn to heuristics based on prior knowledge of the problem to reduce the complexity and reach an approximated solution. However, this would entail a suboptimal solution, especially in noisy data sets, that's specific to the data and not generalizable. Instead, we will add one more piece of information from the specific problem we were originally trying to solve. A single limitation on our loss function. The contribution of each cluster to the overall loss of a solution must be independent of the other clusters, so long as the boundaries remain. The simplest example of such a loss function would be an additive one, where the overall loss is the linear sum of the costs of all the clusters that make it up. A loss function where the age groups on average cover their health expenses holds this condition. On the other hand, if the health insurance policy for babies is very cheap, even though their expenses are very high, and we count on other age groups to cover for them, this condition does not hold. For cases where the objective can fulfill this requirement, dynamic programming can bail us out. Dynamic programming is where an algorithmic problem is broken down into subproblems. The results are saved, then the subproblems are optimized to find the overall result. If you've ever put together a puzzle by starting from the right corner, putting it together, then putting it aside, then doing the left corner, putting it aside, then the tree or the flower in the middle, then putting it all together, you've already done some pretty serious dynamic programming. To apply dynamic programming to our clustering problem, we will have 2 steps. The first step will be to calculate the costs of all possible individual clusters of the order of n squared calculations. That's 28 calculations for our 7 Simpsons characters, for each individual, for each adjacent pair, for each adjacent triplet, and so on. The second step will be to use these saved results from step 1 to solve locally and iteratively. We start from a small section, save the best result, then increase. Let's try this just for the age range of Maggie through Bart. We start from a problem of size 1, a single data point. This is, of course, the trivial problem, and we only have one option to consider. We increase to a problem of size 2. Now we have to consider 2 options between Maggie and Lisa, a single cluster between Maggie and Lisa, or separate clusters for Maggie and Lisa. Same for Lisa to Bart. We compare them by loss and reach the conclusion that babies like Maggie have very different health expenses compared to young children like Lisa, and so we prefer separating the clusters. But for Lisa to Bart age groups, they have quite similar health expenses, and so we prefer a single cluster in their case. We increase to a problem of size 3. Now we have to consider all of the options between Maggie and Bart. But some of these have already been crossed off and need not be reconsidered. Since we already concluded that Maggie and Lisa have very different health expenses, among the solutions where they are separated from Bart and the boundaries remain, we can cross off the blue cluster where they are together. And since we already concluded that Lisa and Bart have very similar expenses, we can cross off the solution in purple and orange where they are separated. So really, we only have to consider 2, not 4 solutions by loss. We conclude that the best solution is where baby Maggie has her own insurance policy and Lisa and Bart have another, and we can use this solution to further solve for the remainder of the age range up until Grandpa Simpson, without having to re-optimize for this section of the age range. To recap, our dynamic solution had 2 steps. In the first step, we calculated n squared calculations of individual cluster costs under the assumption that they were independent, instead of 2 to the power of n costs of overall solutions. And in the second step, we used these saved costs to solve small sections of the age range, then increase and solve larger sections using the previously saved smaller section results. By applying dynamic programming to our clustering problem, we were able to reach a fully optimized solution in polynomial runtime in a process agnostic to the loss function. We can apply this to patient care data to describe the mostly increasing health expenses of the human lifespan, or to driving data to describe the typical rush hour free flow speed pattern in city traffic. Here the polar axis is time of day, the radial axis is speed. Pink and red are the morning and afternoon rush hours. Blue is the nighttime free flow, and yellow and green are the midday and late evening. A major advantage of using ready-made tools is that they are already well-formulated and robust. The loss function in any search problem will determine the result. And so, given the freedom to choose it, whether in the clustering problem we discussed today or any other problem you decide to decompose and solve yourself tomorrow, understanding your problem, what you would like to optimize, and which end cases you may fall to is pivotal. More generally, using the specifics and complexities of your problem to your advantage to tailor a solution can lead to better results and allow you to solve more complex and unique problems altogether. But tread with caution, as this also requires greater expertise in building that solution. What I'm really trying to say here is, with that great power comes great responsibility, but often it's well worth it. That's why we're in the business. Thank you.